Let's look at the quantum numbers for electrons in atoms. And remember that these quantum numbers are derived from our quantum mechanical solution from the hydrogen atom, and then we use these same solutions when thinking about electrons in multi-electron atoms. So there are 4 quantum numbers that we want to think about for electrons in atoms, and we'll look for each one at its name and then the symbol we give it, the possible values it can have, and what this number specifies or indicates. So, for example, the principal quantum number is given the symbol n, and the principal quantum number can have values that start at 1 and move up in integers 2, 3, 4, 5 on up to infinity. And the principal quantum number essentially specifies the shell that the electron is in, and this is related most importantly to the energy. And it indicates something about size, because the higher the n number, the larger the radius will be, and the farther away from the nucleus it will be, and also the higher in energy. The next quantum number is the angular momentum quantum number, and this is given the symbol L. It is obviously related to the angular momentum of the electron in this particular orbital. It starts with 0 and then moves up again in integers 1, 2, 3, but the maximum value it can have is n minus 1. So, for example, if n was equal to 3, the only possible values would be 0, 1, and 2. And this designates the subshell that the particular electron is in, S, P, D, F, and this is really indicative of the shape. Different shapes have different angular momentum. Finally, there's the magnetic quantum number. That's m sub L, and it's related to the energy of this particular orbital in a magnetic field. And the m sub L essentially tells us how many different degenerate orbitals do we have with the same angular momentum quantum number. So, for example, the allowed values there are again integers ranging from L down through 0 to minus L. So if L was equal to 2, the possible values would be 2, 1, 0, minus 1, and minus 2, and there are 5 possible values. So this is the orbitals of a subshell. So for example, L is equal to 2 is the D subshell, and there are 5 orbitals within that subshell. And we can think of, in a hand-wavy way, the magnetic quantum number telling us about orientation. Finally, there's magnetic spin. So magnetic spin is really important when there's more than one electron. It gets the symbol ms, and there's only 2 possible values for the magnetic spin, and they're unrelated to the values of the other quantum numbers. There's only 2 choices, plus a half and minus a half, and that tells us about the spin state, and in some ways we can say the spin direction, but what's really important for spin is that we either have spins that are unpaired or spins that are paired. So here's a quick quiz. What's the maximum possible number of values ml when n is equal to 4? So how many possible values of m sub L can we have for n equals 4? Now you can pause it, think about it a little bit, because in about 3 seconds I'm going to give you the answer. 1, 2, 3. So the answer is 7, okay? Because when n is equal to 4, the maximum value we can have for L is 3, n minus 1. And if n is equal to 3, we have the most possible m sub L values. Minus 3, minus 2, minus 1, 0, 1, 2, and 3. That's 7. L is equal to 3 is the f orbitals, and there are 7 possible f orbitals. What's the maximum possible number of electrons that can have n is equal to 3? So this is all the different combinations we can dream up for quantum numbers that can have n equal to 3. Again, you should probably pause it, think about it for a little bit, because I'm just going to all of a sudden give you the answer, 3, 2, 1. Any given level can have 2 times n squared number of electrons. And that's because we'll discover there are n squared orbitals, and each one can have 2 electrons. So I won't go through it here for n equals 2, but for instance for n equals 1 it's very easy. N equals 1, there's only one orbital. N is equal to 1, L is equal to 0, ML is equal to 0. That's the only choice. And it can have 2 electrons in it. Spin plus 1/2, spin minus 1/2. And so there, you get how many choices? You get 2n squared, n is equal to 1, you get 2. If you go up to n equals 3, then you get 2n squared, which is 2 times 9 is 18. So when we move on from hydrogen into polyelectronic atoms, or atoms with more than one electron, we use these same solutions, but the solutions are now no longer degenerate. So in hydrogen, all of the n equals 2 orbitals are the same energy, the 2s and the 3 2p's. All of the n equals 4 are degenerate. That is, they have the same energy. 4s, the 3 4p's, the 5 4d's, the 7 4f's. But as we move into systems with more than one electron, we have similar solutions, and we number them with similar quantum numbers, but the energies are now different. And it's important to realize that generally the energies are lower, and we don't often talk about the absolute energies, especially of the lowest lying orbitals, but their energies are getting extremely low because we're getting a larger and larger and larger nuclear charge.